Welcome to my presentation. I'm Christoph Anneser from the Technical University of Munich, and I present joint work with Nesime Tatbul, Dave Cohen, Zhenggang, Prithviraj Pandian, Nikolay Laptev, and Ryan Marcus. Today, I would like to introduce AutoSteer, a new framework that enables learned query optimization for almost any SQL database. But first, let's clarify some background and discuss what steered query optimizers are. Database systems usually expose a variety of tunable optimizer knobs, and these knobs often belong to rewrite rules of the rule-based query optimizer. Therefore, these knobs can allow us to change the query optimization of a query from the outside without modifying the database system itself. For example, a database admin wants to improve a SQL query, having a predicate whose selectivity is overestimated by the query optimizer, and therefore the optimized plan uses an index scan. Since the database admin knows that the index scan incurs significant overhead, he hints the database system to not use index scans for that query. For some queries, however, we would also like to combine multiple hints. For example, disable nested loop joins as well. In these cases, we use so-called hint sets. Here, hints come from the database users, or admins, so we call it manual steering. However, there has been also a lot of recent work at database conferences on steering query optimizers automatically. For example, the Bandit optimizer at SIGMOD 2021 and 2 follow-up industry papers at SIGMOD as well. Their general idea is that instead of manually providing hint sets, they are directly integrated into the query optimizer. For example, BAO predefined 48 hint sets for the Postgres optimizer, and every hint set can be seen as a custom query optimizer that generates a query plan. These plans are not necessarily different in all cases. For example, there could be a hint set that adapts only rewrite rules concerning join operators. But if an aggregation query is processed, the hint set doesn't affect the plan's optimization at all, and therefore does not produce a different plan. Next, either a cost model or a learned model predicts the cost of each query plan, and then the cheapest plan is sent to the execution engine and the other plans are discarded. However, these approaches have several limitations. First, database systems usually expose up to hundreds of knobs, and the current approaches consider only a small predefined subset, or they select them randomly. Furthermore, they require a tight integration into the database system's query optimizer, which, in turn, requires a good understanding of the overall system as well. And of course, such an integration is then tailored and customized for one database system and not generalizable. To overcome these limitations, we propose AutoSteer, a more generic way to steer query optimizers. And instead of integrating the steering logic into the system, AutoSteer is an external tool that intercepts incoming SQL queries and does the steering outside the database system. We only need two things to connect AutoSteer to a database system: a text file that lists all the available knobs, and a simple connector, which is usually implemented in less than 50 lines of Python code that connects AutoSteer to the database system. Here you can see AutoSteer at one glance. However, since this overview is a bit overwhelming, I will guide you through the concept step by step. As a first step, we provide the knobs text file, which lists every tunable optimizer knob in one line. AutoSteer will then use this file to automatically figure out what knobs are relevant for a SQL query and could be used for steering. Next, we must also implement a simple connector that provides the following functionality. It must establish the connection to the database system that we want to steer, and it must be able to toggle the knobs and explain and analyze the query plans. Furthermore, it must be able to execute SQL queries and track the execution times. To the right, you can now see a simple base class from which a new connector could inherit. For example, let's have a look at the Postgres connector. Here you can see that the connectors mainly differ in the syntax to toggle knobs and to explain query plans. But of course, AutoSteer also works with an integrated database connector, which would take more time to implement, but is usually more effective than the explain-based generic connectors. Next, we submit a SQL query to AutoSteer. As a first step, AutoSteer calculates a so-called query span, and a query span contains all the knobs contributing to the query plan's optimization. To approximate the query span, AutoSteer uses the database connector to toggle the knobs, and then lets the database system explain the query plan. If the explained query plan differs from the default, AutoSteer assumes that the knob affects the plan's optimization. As a next step, and based on the query span, AutoSteer searches for promising hint sets that improve the query execution time. Therefore, AutoSteer leverages the database connector again to execute the different query plans and track the execution times. The hint set search is based on a greedy algorithm, since there are exponentially many hint sets in the number of knobs. And according to our experiments, most hint sets yield bad execution plans. The greedy search tries to find the most promising hint sets with reasonable overhead and assumes that larger beneficial hint sets are constructed of smaller beneficial hint sets. While this assumption is not always true, it is true in most cases, as our experiments have shown. The input for the algorithm is the SQL query and the query span. In that case, we have a query span with the knobs 1, 3, 6, and 9. So first, AutoSteer uses the empty hint set to execute the default plan, yielding an execution time of 60 seconds. Then, AutoSteer disables every knob found in the query span and executes the resulting query plans. In case a hint set generates a plan that performs worse than the default, AutoSteer discards it. Here, this is the case for knob 3. Next, AutoSteer combines the hint sets from the last step and creates larger hint sets. And again, here also all hint sets perform worse than the default and the greedy search terminates. The proposed greedy search explores several hint sets and alternative query plans that can be used to fit a learned model, for example, a tree convolutional neural network. We call this usage scenario AutoSteer's training mode. After we train a model, we can run AutoSteer's inference mode, which also uses the greedy search, but instead of executing all the query plans, it leverages the pre-trained model to infer query plan execution times at runtime and also to steer query execution at runtime. Furthermore, we can export all the generated query plans and evaluate them later to assess the query optimizer and to find potential problems that can be improved. For a qualitative evaluation, we can also use QO Insight, a visual tool that lets query optimization experts inspect the steered query optimizer and to spot problems. We also present QO Insight at this conference, so please come over to Demo Group B and check it out. Let's now come to the evaluation. We tested AutoSteer with 5 open source database systems and evaluated it using public benchmarks and production workloads at Meta. For example, we used a join order benchmark, TPCDS, Stack Exchange, and a dashboard application at Meta with over 3,000 queries that scan petabytes of data on a daily basis. We also compared AutoSteer to previous steering approaches, but we did not include all of these experiments in this presentation for time reasons, so please refer to the paper for more details here. First, we evaluated AutoSteer's training mode with PressDB using the join order benchmark. AutoSteer explored here more than 1,730 different hint sets and achieved performance improvements of up to 40%, for example for queries 17, B, D, and C. Next, we used the same benchmark and trained a tree convolutional neural network and ran AutoSteer's inference mode to infer the execution times. On average, AutoSteer could improve the query execution by more than 20%. For the dashboard application at Meta, we focused our evaluation on tail latencies, since the dashboard becomes usable only once a large portion of queries have been successfully executed. The workload comprises more than 3,000 queries and processes petabytes of data every day. The figure shows that AutoSteer reduced the wall time in the 99.9 percentile from 50 to 37 minutes. If we had an optimal oracle that always picks the best plan, we could reduce the wall time to 32 minutes. In our last experiment, we compare AutoSteer to the bandit optimizer. We can see that AutoSteer's training mode considers significantly fewer hint sets than BAO, but still meets or even outperforms it in terms of performance improvements. To summarize, AutoSteer is a practical framework to steer query optimizers and assist query optimization experts by automatically finding better execution plans. These plans can serve as counterexamples and help experts to improve the query optimizer's implementation. Furthermore, AutoSteer outperforms previous steering approaches with respect to the exploration time, to achieve performance improvements, and also the applicability to new systems. AutoSteer is open source and already supports 5 database systems, with more being added in the future. We learned also many lessons when we applied steered query optimization in the industrial setting at Meta that we describe in more detail in our paper. That concludes my talk, and I would like to thank you for your attention.